times U inverse W dagger plus W times du inverse times W dagger plus W U inverse dW dagger. Okay, good. Now we just have the differential of the inverse of a matrix to compute. Any takers on that? Well, here's a trick when doing these matrices things. Remember that the 1-by-1 case is a special case of any matrix. And the 1-by-1 case is just the scalar. So at least we can, make a reasonable, intelligent guess by looking at what the 1-by-1 case is. So what's the differential in the 1-by-1 case? Right? It's just minus du times u to the minus 2. Now, one problem we have is, well, that's fine for the scalar case. In the matrix case, these guys don't commute, so I'm not sure what order to write this in. This one doesn't look too symmetric. Maybe it's this plus 1/2 of its transpose, or something. I don't know. But at least I always like to go through that exercise because then when I get my final answer, I can at least do a sanity check. So we'll see how we can get it. Now, what I like about using differentials is the fact that oftentimes something that looks complicated like a function like this, as long as you can write down what the function actually means, then you can just take the differential of that definition and get the differential which you want. So, for instance, what we do know by the meaning of U inverse is that the identity is equal to U times U inverse. That much I think is pretty clear, right? So if we take the differential of this, the differential of the identity is 0, then its product rule is du times U inverse plus U times the differential of U inverse. Right? And now, this is what we want, and we want this in terms of the changes in U, and I can certainly solve now for du inverse. Pretty straightforwardly. So the first piece, then, let's see, I want du inverse, right? So I'm going to put this on the other side of the equation, where it will pick up a minus sign. So I'll have equal to, what does my piece look like? What order did I do today? Minus, right, du times U inverse. And then on that's this guy over there. And then to get du inverse, I just pre-multiply by U inverse. Multiply by U inverse to get du inverse. Yeah, and I buy that, right? That's clearly what we had over there was clearly a special case of this. And since this was a nice symmetric expression, this is nice and symmetric too. So I'm pretty happy with that. Good. Now what's du? Well, du is, du is pretty easy because u was w dagger OW. So du is dw dagger times O times W plus w dagger times do, but O is constant, right? So it's just O and then times dw. Now I think we're in business, right? We've got all the pieces. We're trying to take this differential. So let's gather it all together here. So the differential of the electronic energy is going to look something like, F times the trace of H times dP, and dP had where is he up here? dW, right? Times U inverse times W dagger plus W times the differential of U inverse, which is this guy. So I should make that a minus. inverse here. And then there's du. All right, and I'll get my du in there. And then there's going to be a u inverse, which gives me my du inverse, which had to be followed by w dagger. This may look messy now, but it's going to all turn out okay in the end. And du was dw dagger ow plus w dagger odw. And the final piece was very closely related to the original piece over here, wu inverse dw dagger. No, it's off, but this is where now we get, creative and massage this into some format we like. Well, you'll notice, and it's funny, these kind of formal simplifications are always a matter of art, right? You'll notice there are two types of terms. There are terms that are either dw terms or terms which are dw dagger terms. So we'll gather those together separately. So let's get the dw dagger terms. So I've got f times the trace of h times, I want dw dagger first. So dw dagger times something. And notice by cyclic property of the trace, I can always arrange all of these dw dagger terms to have their dw dagger first. So that'll make something kind of neat and tidy. We'll have to figure out what's going to go on in there. I'll leave some room. I'm not sure how long it's going to get. And then there's going to be another piece. And that other piece actually is going to be closely related to this first piece. This other piece, anyone tell me how it's going to be related to the first piece?
Hermitian conjugate.
It should be the Hermitian conjugate. Why is that? Well, look, the kinetic energy is always real. So its differential has to be a real number. So the trace of this matrix plus the trace of some other matrix has to always be real. So this thing basically has to give the complex conjugate of that. So it should be its Hermitian dagger. Or I should be able to arrange it such. So in anticipation of that, I'll put some big blank guy here, and then the dagger of dw over here. So I'm going to try to gather all my terms into this. Okay, dw dagger. Let's see here. Let's start with this one. So dw dagger. So my plan is I'm going to take this, and he's on the end of the chain here, right? He's got h times this stuff. So that dw dagger is going to flip around to the front, and what's going to be left after him is h, w, u inverse. Okay, good. Now I took care of that term. Where's my other dw dagger? It's a dw, let's say, here it is, dw dagger. So remember, I'm just going to take everybody off the end, flip him around and around and around until I get dw at the beginning. And while I do this, I'm just cyclically permuting, right? So what follows after dw dagger is going to be O, right? So the next, remember my minus sign, so there's going to be minus O, then there's W, and then continuing along, I'm going to hit U inverse next, then I'm going to hit W dagger, then I'm going to find H over here. Then I'm going to find W and U inverse. Like that. Wow. Okay. I guess we can do the DWs now. Okay, so where's my first DW? Here's a DW. I'm going to have put him off on the end, right? And then when I come around the chain, the first thing that I'm going to hit is U inverse. Then I'm going to hit W hat dagger. Then I'm going to hit the end of this bracket. I'm going to hit H. And then I'm going to hit, I'm back to where I started. DW. All right. Let's see, am I getting the Hermitian conjugate? Well, this guy should be the Hermitian conjugate of this, and this looks pretty good. Right? Because H dagger is H, W dagger is W dagger, U is Hermitian. So that piece worked out just fine. Okay. This DW guy. Well, if he's on the end, then the next thing that got hit was this U inverse. And don't forget, I've got my minus sign, so there's minus U inverse. Then there was W dagger. He comes out in parentheses, hits the H, and then he hits the W, a U inverse. Where am I going? I'm going for this guy, right? So there's a W dagger and an O. Times W dagger and O. And is this Hermitian conjugate? Well, on this piece, let's see. U inverse, W dagger, H is Hermitian, W dagger W, U is Hermitian, W dagger, oh, yeah. All right. Good. Whew. So I've got F times the trace of DW dagger times some matrix that I have here in parentheses. And for reasons that will become clear, I'm going to name the thing, and for reasons that will become clear, I call it grad with respect to W dagger. But that's just terminology of the end. That's all these parentheses. And evidently, the rest of what I got was the Hermitian conjugate of this, right? Grad W dagger E, it's conjugate multiplying DW. That's the expression. All right. Now, I guess it's time for us to figure out what this thing gives us in terms of the derivatives, unless there's any current questions. All right, we'll see what, we just keep it simple. Well, actually, maybe as long as I'm making things nice and tidy, let's write this guy down and look at our expression for him, see if we see any common sub-expressions. And notice that we do, right? This piece, HWU inverse, appears here on the end. Right, this guy and this guy are on the end. So let me factor him out. HWU inverse. The first piece, that was just him by himself, I would reproduce with the identity. Then minus, and then these other parts are O, W, U inverse, W dagger. That's it. All right. I should start to maybe ring some bells. We'll ring some bells with that a little bit later on. Just think about that. That looks familiar to you. Okay, but back to my differential here. So that's my expression. So the differential of the kinetic energy equals, apparently, F times the trace. Before I do that. As we've already pointed out, these guys are Hermitian conjugates of each other, right? So the trace of one is the complex conjugate of the trace of the other one. Right? I'm saying that, trace of matrix plus matrix dagger is trace of matrix plus trace of matrix dagger. The trace of matrix dagger, you're just summing the dagger along down the diagonal, is just the trace of them, but you start everybody. So what I have then is this trace plus its Hermitian conjugate, which gives me twice the real part of that trace. So I get F times twice the real part of the trace of dW dagger, grad W dagger. And then we better write this out in terms of its matrix components. So the trace would mean that I would be summing over, the outer index in this matrix product. So I've got dW dagger has certain matrix components. Grad W dagger E has certain matrix components. These usually get indexed by alpha and I. And I have I alpha here. And this is alpha I. It doesn't matter. These are just some dummy indices, but I happen to know that they should line up and give me. And then this would be F times twice the real part, sum over my components, right? So the sum on alpha does the matrix product, and the sum on i's on the outside is doing my trace. I've got here dW alpha I star, almost a dWi, but not quite. Grad W dagger. It's starting to feel like the old joke, never drink and derive. Well, it looks like that's what I've got. We're in the woods right now, but we'll be coming out soon, don't worry. Alpha I, like that. Okay, right? So far, so good. Now, I should just write out what that real part means. Okay, nice, cute little result. All right. What is that real part? Okay, so I've got one complex number times another complex number, with the first one starting. So if I have two complex numbers, say Z and W, and I multiply them, this is going to be what? The real part of Z minus I times the imaginary part of Z times the real part of W plus I times the imaginary part of W. And actually, I want to take the real part of this, otherwise I'll be writing forever. And that gives me what, guys? What's the real part of that problem?
Real part of Z times real part of W plus imaginary part of Z times imaginary part of W.
All right, very nice. So it basically takes like a vector dot product, right? Where you've unfolded the real degrees of freedom in the complex numbers into little 2 vector, which is basically what we're planning on doing. Based on that, that tells me that the differential of my kinetic energy is going to be, well, there's this overall filling thing, which is a factor of 2, and then I'm summing over all alpha and I, and that real part then gives me the real part of the differential of W alpha I times the real part of this gradient thing plus the imaginary part of dW alpha I times the imaginary part of this gradient thing. Like so. And from this then I can pick off the partial derivatives. The partial derivative of the kinetic energy with respect to the real part of my degrees of freedom, which you recall is what we said we needed to be able to compute to do a steepest descent algorithm, right? That, from this expression, is what then, guys? So this is the differential. What's that derivative? take this gradient of v, the real part of that is the partial derivative. There's an extra factor of 2 that's coming in because something to do with our coding complex numbers into real numbers and 2 degrees of freedom into 1 kind of thing. And then there's this extra factor of f, that's just the prefactor to all of my expressions. So that gradient is pretty much just the real part of this matrix object that we know how to compute. And then the the partial derivative, the piece of the gradient that refers to the imaginary parts of the same set of degrees of freedom, you can read off exactly analogously as well. There's the prefactor, then there's the factor of 2 that has to do with the packing of degrees of freedom, and then you have the imaginary part of the gradient of the energy. And one thing that's really neat is notice to carry out our steepest descents algorithm, what we wanted was to be able to pack these 2 partial derivatives into a complex number of the real derivative plus I times the imaginary derivative. And in fact, actually, that packing is already done for us by grad W dagger, because its real part, and if I take this as a complex number, its real part does go in the real part of the derivative, and its imaginary part does go into the imaginary part of its derivative. All right. Good. All right. So let's see, what do we manage to accomplish now? So, and these derivatives, right, we learned corresponding to a differential with our prefactor f times a trace of any matrix times a differential in the density matrix. And for the kinetic energy part, that matrix was just minus 1/2 L. And this then is the derivative in terms of that, say, Hamiltonian operator. It has this kind of expression. So now, I was asking you guys whether this seemed familiar at all. Where does that seem like it's coming from? Where have we seen something like this? Yes.
It's 1 minus OP.
Say what?
It's 1 minus O times P.
Very good, yeah. It's 1 minus O times P. That's nice. Good. Yeah, that's definitely one way to identify it. 1 minus OP, or just P, because we're not used to O's. Right? We just want to try to interpret this thing. Times. So this derivative thing, right, has the Hamiltonian acting on my wave function. This thing, usually the density matrix is some kind of projection operator. So this combination is some kind of projection operator. So I have some kind of projection against the Hamiltonian acting on my wave functions with some kind of normalization. So this is a matrix form of, well, the one state case of this is what variational principle? If I just had one state, what variational principle am I implementing here? Where we normalize the wave function and take the expectation. If it's just one wave function, that's the, maybe you guys don't remember the name, right? That's the Rayleigh-Ritz variational principle. So let's check if we got our algebra right. So the Rayleigh-Ritz, right, says that the energy I get by minimizing over these unconstrained wave functions this ratio. Right? Then they never really quite explained it to you. But formally speaking, what they tell you is then you can set 0, that makes sense, equal to the derivative of that thing. But they tell you to take the derivative for some reason with respect to the product, or the psi stars. You've probably seen them do that to you before, of that energy expression. Well, let's see what we get if we do that. This is evidently this gradient we're supposed to deal with. Well, derivative of a ratio, we know, right? You have the denominator squared on the bottom. And then you have the bottom times the derivative of the top, WW, right? Oh, ci squared. Derivative of the top with respect to that bra formally is h acting on w, minus then the top times the derivative of the bottom, whw, and the derivative of the bottom is just w, right? So let's see if we can simplify this a little bit. There's an overall factor of the normalization. The first term then is just h on w. The second term I could write as the vector w, the ket w, times whw over ww. Like that, right? So let's compare, because this should be the same thing. This should be the one-state case of my expression over there. So overall, I have a 1 over w on w, right? But the overlap of w with itself is u. And I've got, sure enough, a nice u inverse hanging out on the end. I also have, for my first piece, Hamiltonian on my state. And sure enough here, for my first piece, I have Hamiltonian on my state. The second piece has Hamiltonian on my state, right? Collapsed on w, normalized by u, and reconstructed with a w. So what have I got over here, right? I've got my overall u inverse. I have w dagger hw, right? That's basically my whw, my u inverse. Oh wait, I'm sorry. Then I have u inverse times my whw, which is that extra 1 over w on the inside. And I should just have w as a ket over here, and I do. With, whatever, some extra normalizations that we had to carry as a price of our notation here. Okay. So, good. All right. Now we're going to try to get to the other pieces. These will go a little bit more quickly if we draw our main lesson here, which is that from this form, you get the gradient that you need, right, of C electron came out to be, again, it's this kind of, there's a projection. I'm not going to write the whole expression, it's over there. H on W, and then a U inverse. Whatever H appears here, that H goes there, and it gives you your gradient. All right, so what's our next term here? So this was our kinetic energy. This was the electron density coupled to the nuclear potential. And all we want to do is massage it into our new favorite standard form. And remember, by the way, this expression is your code. So that part's nice. Every time we derive one of these things, we've written our code. So the electron-nuclear interaction, potential electron-nuclear. I have it written down over there. It's that second line. Let me dagger out the J, N. So I have N, dagger, J dagger, O, J, V, nu. And I need to take its differential, and I have to remember how it's related to the electronic wave functions. The density, I think I've erased it now. The density itself is diag of the density matrix, which carried some factor of F, fine. The density matrix was I, C, C dagger, or P. Call I dagger. The diagonal of that matrix times F is my density. That has to be daggered with then the rest of this vector, J dagger OJ V nu. Like so. Now, we're very good now at taking the differential of the trace of some matrix times the density matrix. But presently, it appears that our density matrix is inside some diag operator, and there's no trace in our expression. But there's one handy identity. This is the last kind of tricky thing that's very handy in this language that you need to know. And that is, if I have the diagonal vector extracted from some matrix M, and I dagger it into a vector V, believe it or not, that's the same thing as the trace of the conjugate of the matrix times the matrix diagonal, the diagonal matrix composed out of the vector. And if you want to see that, here I'll show you. So my matrix is M, right? Its diagonal components would be MII. I'll give you each of the components. It's starred because this is daggered, and that has to be summed times VI. So the left-hand side is that. This guy here would be then the trace of M dagger, say, I make up some indices here, alpha beta, times, now the diagonal of V would be, to make a diagonal matrix of that, I would make a matrix delta beta alpha, so that I'm multiplying when I sum on betas here. Like maybe I should write this in summation. Sum on alpha beta, right? And then I'm multiplying, then I'm tracing over the outer index. But to make V into a diagonal matrix, I need the Kronecker delta times the components of V. Right? So just as a matrix beta alpha, this thing is diagonal, and when beta equals alpha, the value is whatever B alpha is. So that's the meaning of diag of V. This is, of course, the matrix elements of M, and these are written in the correct order, so when I sum over beta, I'm forming the matrix product, and then I get the alpha-alpha component and sum over it, and I'm doing my trace. And then finally, you just collapse the Kronecker delta, and you find you're summing on alpha, M star, alpha-alpha, B alpha. It's the same. It's the same thing. So those two are related. And then, finally, this thing turns into something nice I can deal with, right? This is F times the trace of the dagger of this matrix. Well, the dagger of that matrix is pretty easy. It's Hermitian, right? First goes I, then P dagger, but P is also Hermitian. I dagger times the diagonal matrix formed out of this vector, J dagger, OJ, V nuke. Like so, right? And now this is in my canonical form, where it's the trace, it's actually even, it's got F, right, times, it's got F times the trace of some matrix times dP. Well, when I take the differential, dV electron nuclear, right, I can cyclically permute this so that I've got a bunch of stuff occurring before P, right? And it'll be in exactly the same form with a dP because I'm taking the differential of this. And so I will have precisely this gradient, but now H will be a different matrix. That's all. And so you can call that the Hamiltonian part associated with the electron nuclear part, I suppose. And what will that H be? Can we read it off of here? H is the stuff that would be before P in the trace. And right now, P in my trace is sitting right here. But I know how to do sigma permutations, so I know how to do them. I presume you guys do. So help me out. What will be the first matrix that'll start off the sequence. If I manage to get that P on the end. Right, it's like shuffling cards, right? So this one will go on the end first, right? So I'll be sitting there. Then this one I will peel off. And then my P will be on the end. And what's left will start off with I dagger. Right? So I dagger, diag of whatever this thing is, J dagger OJV nuke. It's clearly some representation of the nuclear potential times I. Like that. And we can also start to make some sense out of these expressions, right? Previously, when we did the kinetic energy operator, this thing really does look like a piece of the Hamiltonian. It's minus del squared over 2. Okay. This must represent the action of the nuclear potential on my wave functions. And let's see what happens. So I have my wave functions, which are some coefficients, right? The first thing I do to them with I is I put them into real space samples. So I get psi of x. Then I multiply by a diagonal matrix. So if you have a vector and you multiply by a diagonal matrix, all you're doing is you're going down the list, right, and multiplying. So that's like taking my wave function and multiplying by some function, which I'll call v nuke of x, right? And in fact, look, that's what this is. This is basically v nuke. I did some kind of transform on it, multiplied by O, did some other kind of transform on it. It's putting in the right normalization factors and things that I need for my language. And then the last thing I do is this I dagger, evidently, right, is bringing it back into my coefficient space representation. And in the Fourier case, that's actually very clear. You might remember that I is the Fourier kernel, right? I dagger, because the Fourier kernel is symmetric, is F star. Right? It's F star transpose, but F is symmetric. And F star is, apart from normalizations, it's just the inverse transform. So this thing puts me into real space, multiplies by some normalized version of the nuclear potential, and transforms me back. And the nice thing is, though, this takes care of all the normalizations for you. We know you're supposed to do something like that. But when you code it up, sometimes it's not clear how things are normalized. But here, in this language, it is. Okay, so that's the derivative of electron nuclear. That was the differential of this piece. How about, oops, I forgot parentheses here. All right, I'm good here. So now we need this part here, the mean field electron-electron interaction. So we should find the H that goes with that one. So the Hartree potential energy is 1/2. Well, I'll dagger out the J for you. I've got to dagger this here. So I've got N vector J dagger O, and then phi. Like that. So we should remember what phi hat is. And so 1/2 N hat dagger, J dagger, O, and phi hat, if you recall, was L inverse on the right-hand side of Poisson's equation, which carried an extra factor of -4 pi. I'll just put that here for now. And then O on J of N. And as I've commented before, actually maybe I'll keep my front box over here, so this at least is phi hat again. Right. Okay, so I need the differential of this. And it's going to lead once again to some effective Hamiltonian. vectors on the front side? Well, let's see. How many pieces am I going to get when I take the differential with respect to n? How many terms? 2, right? See someone on 2, right? I'll have this term when this is a dn, and this term over here when this is a dn. And ultimately, what are those 2 terms going to give me?
Maybe Hermitian conjugates equation.
Yeah, but Hermitian conjugates, and the whole thing's real anyway, right? So both of those terms are going to give me the same thing, right? Another way to see it is that this kernel inside here is Hermitian. So they're going to give me the same thing. So that will kill off my factor 2, right? So basically, I'm looking at dn dagger, right? J dagger O, and I can write all this stuff out, or I'll just call it phi hat, right? So I'll get that. That's the usual, like, Hartree derivative kills the 1/2, and you just get the other piece. Now from this, and the experience we had here with the electron nuclear, where again I had n times now some vector, so dvln was equal to dn times some vector. We should be able to pull off what this h is, sort of by analogy. So you guys give me a hand on that one. This guy gave me that. So this guy, with this vector, should give me what in relation to this?
The diag for the...
Right, exactly. So I'll get the same thing, but inside the diag, my vector is going to appear. And my vector in this case is this fragment here, J dagger O phi hat. Nice. Good. All nice and properly normalized for us. All right, we're cruising along, I think. And there is the exchange correlation energy piece. It's the last piece of the whole shebang here. It's N dagger, J dagger, O, J, EXC on N. Okay. So we're going to get, again, 2 pieces. I have to be a little careful now. I'll get dn vector dagger, J dagger, O, J, EXC of N, plus N dagger, OJ, EXC, D of EXC. What will the first term give me? So, the effective Hamiltonian that goes with this exchange correlation thing, it's going to have 2 parts, and I'm asking for what that part will give me. I see smirks, so maybe it's just so obvious. All right. Well, it looks just like this, right? But we had this vector then, and we've got this vector now. So there's going to be an diag, and that vector we'll copy down just for officiality's sake, was J dagger OJ EXC on N, plus, then we fill this in, we can end our lecture. So we'll have all the derivatives. Now, what is that thing? What is that guy? It's this one here. But we have to deal with this differential. So the differential of EXC of N is? That's the $1 million question. Well, we better get back to definitions, right? So the pth component of that is the differential of exc evaluated on the pth component of n. Right? That's just the definition of the component of that function. This, by differential calculus, right, by the chain rule, is partial exc at np with respect to np times dnp at that particular point. Well, shorthand, well, what the heck? This is exc prime at np times dnp. And we had just commented on this, right? If I'm taking two vectors and I'm running down all the points and doing a pairwise product, that's the same thing as taking one of those as a column vector and the other one as a diagonal matrix and multiplying the two, right? So this looks like the diag of exc prime of n vector, that makes that nice big diagonal matrix, times then dn vector. Then I'm in business to get my differential into my favorite form. So my remaining piece, what am I going to call that? Sorry, I got a little tired at the end of this. So the second piece of exc, right now stands at n dagger j o, no, it should be a j dagger, j times my differential. My differential can be composed of a diagonal matrix of the derivative of the exchange correlation field on my vector, multiplying dn, and I have to try to figure out then what h would correspond to that piece, which then I will write here. We'll have all of our parts. Okay, so you guys tell me. And by the way, this is the last piece of hairy algebra in this course. Once we get this, we've got all of our expressions and it's just our code. So, home stretch here. Mental processing, cross-checking. Well, what will the overall form be? Right, what were you thinking, Matthew? I saw your point. What were you thinking?
Rearrange it with taking the end of the whole thing.
Right, because look, these are all nice real vectors. Right, everything's here is nice and real. So I could rearrange this guy into my favorite form, right, by daggering the thing. Now, this guy is the diagonal matrix of a real vector, so its dagger just gives me himself back again for that one. And I've got j dagger, O is Hermitian, and I've got jn. Good. I like that. And then so for this guy, what about that guy? Is that in our standard form? Yes, right? Of a dn times some vector. And we know what happens then. We just get, where's it? This guy with our vector in the middle. So that's I dagger, diag. Our guy in the middle is, oh man, it's this thing here. It's another diag inside the outer diag, right? So there's the diag of this exc of n, kind of funky thing, multiplying, doing this thing over here, j dagger oj n. Then that turns into a matrix, and then multiplies by, like so. What does that mean? Well, once again, I take my wave function, I put it in real space. I pointwise multiply by some field, which we'll think about in a moment. And then I transform back to coefficients. And the vector field that I do is basically my density, treated by a couple of transforms in here that in plane waves don't do all that much. J and J dagger, by the previous arguments, are basically inverses of each other, and O is the identity in a plane wave basis. So in a plane wave basis, this doesn't do anything. In other bases, it does something that's non-obvious, but more or less represents your field back again. So I just am taking my density, somehow modified appropriately so I can minimize the energy. And then it gets pointwise multiplied by this, chain world partial derivative. And that makes some effective potential field. And then that gets applied to my vector. So that's what that piece gives us. All right, good. So that's it for the algebra. And as I had promised, deriving the algebra is writing your code. So all these expressions are on the assignment for you. This is a lot of writing. It could be little mistakes here and there. So you just have to code them up as they are transcribing in the software. So good? All right, guys, that's it for this one. So next time we meet in the basement, right? And then we'll talk about more powerful minimization methods down there since we've got our